Many times when you're doing problems with math, you end up with a fraction, such as a fraction might be 4 over 12. And your teacher says, hey, you need to reduce that. Don't leave it as 4 over 12. So you go, oh yeah, that's equal to 1/3. Okay? The same thing happens with chemistry sometimes, is there's two different ways to write the formula of a compound. There's what's called the molecular formula, and there's what's called the empirical formula. Okay, the molecular formula is the real formula. Okay, it's used to show the exact amount of each atom in the compound. Okay, and again, a lot of times I use this word right here. It's the real formula. Okay, what's the real formula of glucose? Is C6H12O6. Okay, what's the real formula of hydrogen peroxide? It's H2O2. But another thing you can do is you can say, hey, I don't want the actual formula. I want you to reduce those. If you can reduce those numbers, I want you to reduce those down to the lowest, just like here, the lowest whole number ratio. Okay? And that is called the empirical formula. So we look at something like glucose here and we go, okay, glucose C6H12O6. What's the biggest number that will go into all three of those numbers is the number 6. So we divide everything by 6, and what do we get for the empirical formula? Just CH2O. Okay, with hydrogen peroxide, they both have 2's, so we can divide them both by 2's, and what do you end up with? Just HO. With C2H4O2, again, what's the biggest number that goes into all of those? Is the number 2, so we just cut all those numbers in half, and we get CH2O. And sometimes the molecular formula will be the same as the empirical formula. NF3, nitrogen trifluoride, is NF3. That's the molecular formula. And its empirical formula is also NF3. And many times that happens, such as a big molecule, such as C17H21NO4. If any of those are prime numbers, like that right there, or if any of the numbers are a 1, like there's only one N, well then certainly you can't reduce that. And so that right there is the molecular formula. It's also the empirical formula. So just remember, the molecular formula is the real formula, well, the actual formula of that compound, where the empirical formula just shows the ratio. It's basically the reduced version of the numbers in that compound. Okay, and obviously to convert from them, we already talked about them, you divide each subscript. These little numbers down here in the bottom, those are the subscripts. So you divide each subscript by the largest whole number that all subscripts are divisible by. Okay, just like when you reduce a fraction, what's the biggest number that will go into all of those numbers? Okay, with C6H12O6, the largest number that divides evenly into those three numbers is 6. So you divide by 6, and then sometimes remember that the molecular formula and the empirical formula are the same. So example number 1 here says determine the empirical formula of the following compound. So here's where you might want to pause the video and give this a try yourself. See if you can do this, and then come back to the video and make sure that your answers are the same as mine. So on letter A here, we've got N2O4, so that's 2 N's and 4 O's, so I can divide that by 2. That would give me an empirical formula of NO2. This one's a little bit trickier, but if you think about it, it's got 2 C's, it's got 4 H's, and it's got 2 O's. Even though they're separated out, that's how many it has all total. So that one also we can divide by 2, and that would again give us CH2O, like our glucose example earlier. And that does happen a lot. It does happen where a lot of very different compounds will end up having the same empirical formula. Again, just like up here, glucose turned into CH2O as well once we divided and got the empirical formula. Okay, letter C, notice we have a 3, and then we also have just 1 phosphorus, so there's nothing we can do with that, so that can't be reduced, so it's just Na3PO4. Here again, we can divide both of those numbers by 2, so that would give us C3H7. And then this one, I actually showed you that example earlier, C17H21NO4 has a prime number here, and it has a 1 right here, which two reasons why it cannot be reduced. Now, what if you're going backwards, though? What if they give you the empirical formula, so they give you this one, but then they ask you for the molecular formula? In order to do that, because just like with any fraction, if you have 1/3, well, okay, what's the real fraction? Well, it could be 2/6, it could be 3/9, it could be 4/12, and we could keep going forever, right? So you can't just say, okay, the empirical formula is this. What's the molecular formula? They have to give you something else, okay? And the something else they have to give you is you must be given the molar mass of the molecular formula. If they give you that, then you can go from the empirical formula back to the molecular formula. And let me show you how you do that, okay? So let's look at example number 2 here. It says a compound with an empirical formula of C3H4O3 has a molar mass, so that the actual compound has a molar mass of 264 grams per mole. What is the molecular formula? So the first thing that we're going to have to do is take the empirical formula and figure out its molar mass. Okay, so we take the mass of carbon, which is 12, we multiply it by 3, and then there's 4 hydrogens, and then 16 times 3, which is for the oxygens, and that equals 88 grams per mole. So that means that the empirical formula has a molar mass of 88 grams per mole, and the molecular formula has a molar mass of 264 grams per mole. So then what you have to do is we divide them. So you divide those two numbers. You take the mass of the molecular formula, you divide by the empirical formula, and it tells you that it is the number 3. So that means that each of those subscripts, not coefficient, that's not the right word there, each subscript in C3H4O3 must be multiplied by 3. So notice basically I'm just going to distribute this 3 through here. So we end up with C9H12O9. Now, every time you do this answer right here, anytime you divide those two numbers, that must be a whole number. If it's not a whole number, then you made a mistake somewhere. Or maybe I made a mistake writing the question, okay? But that number has to be a whole number. Okay, so example number 3 says C5H9 is the empirical formula for a compound with a molar mass of 138 grams per mole. What is the molecular formula? So again, start with the empirical formula. And this is a good idea, again, to stop right here, check and see if you know how to do it, and then compare your answer with mine. So the first thing I'm going to do is the molar mass of C5H9 is 12 times 5 plus 1 times 9 equals 69 grams per mole. And then the empirical formula is 138 grams per mole. So 138 divided by 69 equals 2. So that means for that compound, I have to multiply everything, all of those subscripts, by 2. So that becomes C10H18. Okay? And that is the correct answer there. That is the molecular formula. Okay, example number 4, and this is our last one here, is the empirical formula for benzene. And benzene has a molar mass of 78 grams per mole. What is the molecular formula of benzene? So again, start with CH. What's the molar mass of CH? Carbon is 12, and there's only one of them. Hydrogen is 1, and there's only one, so that equals 13. And then we take the molar mass of the molecular formula, we divide by the molar mass of the empirical formula, and that equals 6. So that means we're going to take that CH and we're going to multiply each subscript by 6, which gives us a final answer of C6H6.